Thank you very much indeed, Andy, and welcome back to part 2 of the BAA Autumn webinar today. I hope that many of you were able to watch the presentation by Brad Gibson this morning. And as he mentioned several times in the talk, that hopefully the two talks together today will bind together and give you a better understanding of where we are as far as the research on the universe is concerned. So Dr. Andrea Font has agreed to speak to her. She's a computationalist astrophysicist in the Astrophysics Research Institute of Liverpool, St John Moores University. So very warm welcome to Andrea, and her title of the talk is on the screen already. Stumbling in the Dark, Searching for Dark Matter. So without further ado, if I may pass you over to Andrea, and thank you very much indeed.
Thank you very much, Alan. I'm going to tell you about a long-standing quest for finding dark matter. And why Stumbling in the Dark? Why this title? Because after 90 years since it was first theorized to exist, we still haven't found dark matter. So in this talk, I will not give you any final answers, unfortunately, but I hope you'll get a glimpse into the huge effort that's been put by scientists all over the world for finding this matter. And also, I hope that you will learn about some of the open questions that still remain about its nature. So I'm going to tell you about what we think dark matter is and why is it important. What evidence do we have that it exists? Also tell you about a few experiments that are ongoing for detecting it, and how we can use astrophysical probes like galaxies, for example, to understand its nature. So why do we care about dark matter? One reason is because it's the most common form of matter in the universe. Very precise measurements of what done in the universe show us that about 3/4 of the, if you like, mass and energy budget of the entire universe is made of some mysterious form of energy that we call it dark energy, and which we know very little about, and I'm not going to talk today. And the rest is made of matter. And out of all of the matter in the universe, dark matter makes about 85%. So this vastly outweighs the normal matter that you and me are made of. That means protons, neutrons, electrons, and so forth. So to just give you an example, just as I speak right now, billions and billions of dark matter particles are supposed to pass through you and me unimpeded every single minute. So if you want to understand what most of the matter in a universe is, we need to understand dark matter. Okay, so as I said, we have been looking for it for a very long time, and we haven't found it. So obviously we need some help. So here are some of the characteristics to look out for. So one, it is everywhere. Now it is true that it's most likely to be found near galaxies and big structures in the universe, but it really permeates the whole space. So second, we call it dark, but it doesn't mean it's black. A black object still absorbs light, but the dark matter does not emit or absorb light at all because it doesn't feel the electromagnetic force. So maybe a better name for it would be invisible matter, if you like. Now third, we know it interacts through gravity, and that's about it. It may be possible to interact via the weak force. Now the weak force is the force that's responsible for the radioactive decay of atoms. But we don't know for sure that it feels this weak force because all the experiments that have been set up to date to test this haven't found anything yet. Another fun thing about dark matter, we know that it can bend light. Now this is because big clumps of dark matter can curve the fabric of space-time through their gravity and force the light to bend as well alongside. Now, dark matter is known to be crucial for the formation of galaxies. And in fact, the existence of our own galaxy, the Milky Way, and all the other galaxies, and possibly ultimately of life, it's due to dark matter. It can also have a darker side. It can destroy galaxies by leading them to crash into each other. So with dark matter, we're really in the dark. We might be ending up like this proverbial person who looks for his keys under the lamppost just because that's where the light is. Only though in the case of dark matter, it actually makes more sense to look for it where there's light, because luminous objects like galaxies, for example, tend to cluster around dark matter. So we have more of a chance to observe it where there is light. So in fact, this is how dark matter was first observed. And here I want to emphasize the word observations in a sense of gathering of evidence for it, not necessarily in the sense of actual detection. Well, dark matter was first mentioned in the early 1930s by Fritz Zwicky, which was a Swiss astronomer working at Caltech, and you can see him now with his beloved telescope. And he was observing this cluster of galaxies called the Coma cluster. And when he noticed that the galaxies were moving much faster than they were expected to. So for this, he used a formula that says that the more mass there is in a system, the faster the objects move. So by summing up all the masses of all the galaxies in this cluster, it was still not enough for him to explain the high speeds that this galaxy had. So Zwicky came up with this idea. There was some form of unseen matter that was responsible for this extra mass, which he himself coined dark matter. Now, just about the same time in the early 30s, there was another hint for the existence of dark matter, this time from our own galaxy. In 1932, this Dutch astronomer called Jan Oort was measuring the motions of stars near the sun. Now, the stars in our galaxy orbit around the center, but they also wobble up and down a bit because they're pulled back towards the plane of the disk by all the matter there is in between. So Oort went to calculate the accelerations towards the plane of the disk, and he found out it was, again, much higher than he expected, even after accounting for all the stars in a disk. So he also hypothesized that there was some form of hidden matter. He didn't call it dark matter. He wasn't sure whether that was it. Well, his observations were not very precise back then because in the early 30s, there were no good instruments for detecting the coal gas or the dust in our galaxy, which we know they also can emit some light, but they're very faint, so they're very hard to see. So to be honest, these observations are still very imprecise today, and we still don't know for sure whether we need dark matter in order to explain the motions of the stars near the sun. Now, I mentioned this story because this story took a curious turn recently after some computer simulations made some predictions for the existence of a dark disk alongside the stellar disk of the Milky Way. And that would be present in the Milky Way and in any other galaxies as well. Now, if dark matter is shaped, at least locally, in a form of a disk, this could have an effect on the motions of stars. It could have an effect on the motion of the sun itself, but also on the motion of objects inside the solar system. Now, this has even led some people with the idea that the dark matter might have been responsible for killing the dinosaurs. So how this idea might work? Well, it was suggested that every time the sun passes through the plane of the disk, where the dark matter is denser, the outer edges of the solar system become a bit destabilized, and this may lead to some asteroids launching towards the Earth. So now I should say that this idea is quite speculative and it hasn't been proven yet, but and of course there are other valid theories for how the big dinosaurs disappeared. Now, so back to the Zwick's idea about dark matter. So this did not get much traction until the early 70s, when Vera Rubin, shown here, started to look at the rotational spiral galaxies. So this animation here shows the same galaxy rotating without dark matter on the left and with dark matter on the right. And you might not see a big difference first between the two. They all look similar. But if you look closely, you'll see that the outer parts rotate much faster on the galaxy on the right, the one with dark matter. So this is essentially what Vera Rubin was seeing with her galaxies. She saw that the stars were moving much faster than if they were pushed into orbit just by their own gravity. So these observations can be explained if the galaxies are embedded into a massive halo of invisible matter, which makes them spin faster because it adds all this extra mass in the outer parts. So I said that dark matter can bend light. In fact, all matter does, as we know from Einstein's general relativity theory. Mass curves space. So, and the light just takes the path of least resistance along this curved surface. Now, in clusters of galaxies where there's a lot of dark matter, the space is curved significantly. So an image of a bright object behind a galaxy cluster, let's say an image of a galaxy or of a quasar, becomes significantly distorted, just as it would be seen through an optical lens. So in fact, these systems are actually called gravitational lenses for this reason. Now, these systems are very useful to measure the hidden mass between us and the observed bright object, because the mass can be inferred from the geometry of a lens. Now, I'm not going to go into too much detail, but through studies like this, we know that there are huge quantities of dark matter around galaxies and around galaxy clusters. Another evidence for it comes from this system called the bullet cluster. These are in fact two galaxy clusters which are smashing into each other to create an even bigger galaxy cluster, if you like. Now, this image is a composite of three different types of observations. One image is optical, showing where the galaxies are. And the next one is a map of a hot gas which emits X-rays. And you can see there are two peaks in this map which trace the halos of hot gas in the colliding clusters. Now, one of them is distorted in the shape of a bullet, hence the name of the system. Now, this gas takes this particular shape because it's dragged down during the collision and loses some of its energy. Now, dark matter, on the other hand, feels only the gravity of the two clusters. So the two dark matter halos pass right through each other without getting distorted. So, by the way, this image or this map has been made with the same gravitational lensing method that I was describing earlier. So it's not an actual detection of dark matter, is a 3D reconstruction based on gravitational lensing. So something odd is going on. Dark matter cannot be like any of the normal matter we know of. Otherwise, it would be in the same place where the gas is. So some people consider this bullet cluster as being the strongest evidence we have for dark matter, because this type of strange behavior cannot be explained by any other theory. So here's again this composite image of this bullet cluster, and on the right, there's a computer simulation showing the collision of two galaxy clusters. And each galaxy cluster is modeled as a hot halo embedded into much bigger dark matter halo. Now, as you can see, the model matches very well the observations. So at the beginning, I've told you that we know how much dark matter there is in the whole universe. So how do we know that? Well, one way is to measure all the masses of all the galaxies and galaxy clusters in the universe and add them all up, which we can do through various methods. But the more precise measurement comes from the analysis of this so-called cosmic microwave background radiation. Now, this is a diffuse radiation that is left from the Big Bang, and it permeates the whole space. It has roughly a temperature today of about 2.7 degrees Kelvin. But the temperature is very uniform all around us. But here and there are some very tiny variations in this temperature. Now, these variations are shown in this map as the red and blue spots. The red ones are just a little bit warmer, and the blue spots are just a little bit colder than the average temperature. Now, from the properties of these spots, if you like, we can find out how much dark matter there is in the whole universe. To be a little bit more specific, astronomers can turn this map into a type of function, which is known as the power spectrum. Now, this function has some well-defined peaks, and the location and the locations and the sizes of these peaks are very sensitive to the cosmological parameters that go into our models. And one of these cosmological parameters is the density of dark matter. So that's how we know how much dark matter is in the whole universe. Now, another piece of evidence, an important piece of evidence that comes from this type of observations is that if the dark matter is a particle, it must be a very stable one. Now, these observations from the CMB, the cosmic microwave background, tell us that the dark matter was present right at the Big Bang. Now, we know that dark matter is present around us today in the same amount, so that means it must be very stable. That means it cannot decay for a considerable time, at least for the age of the universe. So, before I go into more exotic ideas about what that dark matter particle might be, let me address the obvious question, which is often asked. Isn't this just normal matter, which for some reason we cannot detect with our instruments? So in astronomy jargon, we say, we ask whether this matter could be baryonic, meaning it's made of baryons, like protons and neutrons, and so on. So indeed, people have looked at whether very faint objects could account for the missing matter. This could be brown dwarfs, it could be dead stars, stars that finished their fuel and they're now dead. There could be rogue planets, planets that escaped their solar systems and they're roaming free through space. It could also be cold gas or dust, which we know that they exist in the universe, but they don't emit much light, so they're very hard to see. Primordial black holes are also a possibility. Now, these are black holes that formed just after the Big Bang, and they're not so tiny. They have some mass that means they haven't evaporated yet. Well, so it turns out that most of the compact dark objects, as we call them, add up only to a small fraction of only a few percent of all the matter that's unaccounted for. The more massive objects called MACHOs, which stands for Massive Compact Halo Object, they can be ruled out as being dark matter through a method. Well, people have looked at this with the method of, which is very similar to the gravitational lensing method that I described earlier. So for example, in this image here, if you have a dark compact object that passes in front of a star, it bends the light and it leaves a particular signature in the star spectrum, which can be measured. So we can count all such events in our own galaxy. And it turns out there's not enough of them to account for all the dark matter. However, I should say that the jury is still out on these primordial black holes, which I mentioned earlier, but we know very little about them. We don't know how they form or how massive they should be. Okay, another obvious question is, and you might ask, is whether we are misunderstanding how gravity works. So for example, instead of assuming that galaxies are surrounded by these dark matter halos that no one can see, could we not tweak a bit the Newton's laws of gravity? Now, this is actually a valid question. Now, mind you, Newton's laws of gravity have been tested numerous times and always found out to be valid, at least in the limit of when the speeds are not near the speed of light. But it is possible that on very large scales, like scales of galaxies or clusters of galaxies, these laws could be quite different because we haven't tested that yet. So for example, if you make the gravity just a little bit stronger, you need less mass to keep stuff together. So there are several theories that have been proposed to modify gravity. And the first one has the simple name of modified Newtonian dynamics, or MOND. Now, MOND has been shown to match quite a lot of things, in particular these flat rotation curves that Vera Rubin was seeing, and many others after her. So this can be counted as a success. However, MOND and other theories that rely on modifying gravity still need some developments in order to prove they can explain all the observations that we have in the universe, which dark matter can explain so well. So we haven't ruled dark matter yet, just based on this. In particular, the bullet cluster that I mentioned earlier is still a challenge for these modified gravity theories. All right, so if dark matter is a particle, which is a big if, we can ask first whether it's one of the fundamental particles of normal matter, because we know there's lots of this. Now, you don't have to know what all these particles are. This is a family portrait, if you like, of all the particles in the standard model of physics. They include the quarks, shown here in purple. Quarks are the building blocks of atoms. Then we have the leptons, shown in green. These are very light particles like the electron or the neutrinos. Then we have some particles which we call bosons, and these are the force carriers that are responsible for the four fundamental forces in nature: the gravitational force, the electromagnetic force, the weak and strong force. So these bosons mediate these forces, even though they're particles. And then there's this Higgs boson, which has been discovered more recently. But we can cross out some of these particles out because we already know that dark matter must have some very weird properties. So as I said before, it doesn't interact via the electromagnetic force. So we can cross some of these particles out. We also know that it doesn't feel the strong force either, because we have ways to measure this in colliders and we haven't seen it. So we can cross some more particles that feel the strong force. Then we can require that this particle should be stable, as I said earlier, that is not to decay too fast. And then we lose some more particles which are very massive and they decay very fast. So it doesn't look good. We're only left with neutrinos, which seem to fit the bill, but they are moving way too fast to be dark matter. Now, they move to nearly the speed of light. Now, computer simulations have shown that if dark matter particles move with the same speed as neutrinos, which is near the speed of light, we'll end up with a universe which has very little structure today, which is not what we see around us. So it looks like none of the known particles we know of are the ones they were looking for. But there is some hope, at least from particle physics side. There's this beautiful theory called the supersymmetry, which predicts that all particles in the standard model have a shadow counterpart. And these new particles, no one had seen them, but they would be more massive. The reason we haven't seen them is because we need more energy in order to produce them. At least that's what we believe. Now, the hope is that dark matter would be one of these particles. The supersymmetry is an extension to the standard model. The standard model is the tested one, and supersymmetry hasn't been completely proven. Now, these particles are called WIMPs, which stands for weakly interacting massive particles, because we believe they interact via the weak force and because they're massive. So there's a whole possibility of WIMPs of different masses and different properties. They're all under the same name. But so far, no WIMPs have been detected, even though there have been many experiments going on, but there's still, the experiments are still going on and they're getting improved every year. So there's still some hope to finding these WIMPs, but it's true that the time is running out for WIMPs. Now let me say you a few words about this type of experiments, particle physics experiments, how they work. There are three main categories which are represented in these three diagrams. And the way to read this diagram is always from left to right, and that would be the time evolution. Now, in short, these three categories are known as make it, shake it, or break it. And the first type of experiments is trying to make dark matter. We know from Einstein that we can turn energy into mass and vice versa, to the famous equations E equals mc squared. So, but for example, by smashing two protons into each other at very high energy, we can create a pair of dark matter particles. Now, the second approach is to detect dark matter directly. If the dark matter particle bumps into a normal particle and shakes it, or in physics jargon, we say that it scatters off it, we can measure this impact. And the third one is to break it. If two dark matter particles collide and annihilate, they could give out some light or some normal particles, which we can also detect. So the make it part needs big colliders like this one at CERN. Now, obviously, when we smash particles at very high energy, all sorts of other particles are produced at the same time. So most of these particles are known. So the trick here is to look into all of this debris and separate the unique signature of the dark matter particle. But so far, all the reactions that we have seen at CERN only involve normal matter. So none of them is showing any evidence for a new dark matter particle. But I should say the search continues. And as I said, there's always improvements, maybe go into a different regime of energies to find these particles. For indirect detection, where dark matter particles are supposed to collide and annihilate, there are already instruments in space, like this Fermi Space Telescope, or aboard on the International Space Station. There are also telescopes on the ground, like the Cherenkov Telescope Array, or the CTA, which will become operational very soon. And we hope it will be able to detect gamma rays from dark matter if they do annihilate. Now, with computer simulations, we can make predictions about where most gamma rays may occur from the annihilation of dark matter. Now, these maps are some gamma ray maps from simulations that model the formation of galaxies like the Milky Way, which were produced by our own research group. The map on the left shows the expected gamma ray signal from the center of the Milky Way, and the one on the right shows the signal that may be detected from dwarf galaxies that orbit around us. Now you can see that the center of the Milky Way has a much stronger signal. This is because there's a lot of dark matter in the center of our Milky Way. But unfortunately, the center of the Milky Way is also full of other sources of gamma rays coming from supernovae or pulsars or stellar sources. So for observers, it's quite hard to identify whether the gamma rays come from dark matter or from stars. So they could rely on simulations like these to tell them, to give a better idea of what to expect to detect. Now, as you see, the dwarf galaxies give out fewer gamma rays, but the signal is less contaminated by these stellar sources in our own galaxy. So these tiny galaxies might actually be a more suitable target for the gamma ray telescopes. And finally, as I'm mentioning, the direct detection experiments. These are trying to detect signals from dark matter particles that may be bumping into normal matter. like atoms or nuclei. So this shown here, just two of such experiments. There are many of them. One is using a solid lattice, and one is using liquid xenon. They're called cryogenic dark matter surge and Lux Zeppelin, or LZ. Now, the dark matter particle, in principle, could shake this lattice if it bumps into it, or and if it shakes, it could give out some heat, or it could kick out an electron of an atom, and that would result into an ionization or into an electric signal. Likewise, with the Lux experiment, we can also detect this impact as an electric signal. But the challenge with these experiments is that dark matter does not interact very often with normal matter, if at all. So one has to wait for a very long time to get a detection. Also, the targets have to be very still, and background noise has to be kept to a minimum. And when I say background noise, I'm not saying just the environmental noise, but also the internal noise of objects. For example, they have to reduce the internal jiggling of atoms themselves, which happens quite naturally. So for this reason, this experiment, it takes place at very low temperatures, nearly the zero absolute. So this is a very sophisticated experiment, very hard to achieve zero absolute. Now, these experiments also need to take place in isolated environments, in order to reduce the background noise. And there are all sorts of events that could give false signals, false detections of dark matter. For example, the radioactive decay of atoms in some materials is also contributing to a false signal. Even cosmic rays are a problem. Now, cosmic rays are very energetic particles that come up from outer space. They could be generated in the sun or in other galaxies. So for this reason, many experiments are deep underground, such as this one in the Volby mine in the UK, which is more than 1 kilometer deep into the ground. Now, to say that some experiments are also trying to detect dark matter at the South Pole, which is also a fun place to work. And now I want to switch gears a bit and tell you about how we can use the tiniest galaxies we know of to constrain the nature of dark matter. These are also known as dwarf galaxies, and there are many of them seen orbiting around our own galaxy. But first, let me show you an image of our neighbor galaxy, Andromeda. Now, this galaxy is relatively nearby, at least in astronomical terms. It's about 3 million light years away from us. So it can be seen on the sky quite easily with some equipment. The image on the right is taken with the Hubble Space Telescope, and it shows this galaxy in much more detail. Now, Andromeda is a spiral galaxy just like the Milky Way. So by looking at it, we can get an idea about how our own galaxy might look like if we look at it from an outside point of view. Now, this galaxy and others, this galaxy is supposed to be embedded in a massive dark matter halo. Now, this image here might help you imagine how that dark matter halo might look like on the sky in comparison with the stellar disk of Andromeda. Well, this image is actually a bit of a cheat because it shows the gas halo, which has been mapped recently. But we know that a dark matter halo is just as big as the gas halo. So our main theoretical model, which is also known as the standard cosmological model, predicts that every single galaxy should have a dark matter halo, which is always larger and more massive than the stellar component. It also tells us that the universe has a hierarchy of galaxies. That by this I mean there are fewer large galaxies and many more smaller galaxies. And it also predicts that galaxies like the Milky Way and Andromeda should be surrounded by many small galaxies, which we call satellite galaxies. And each of these tiny galaxies should have their own dark matter halo. Now here's an image of two such satellites. You probably know what these are. These are the large and the small Magellanic Clouds. They can only be observed from the southern hemisphere, though. These are among the largest satellites of the Milky Way. So they have been known for quite some time. And they too are expected to have dark matter halos. Nowadays, with bigger and better telescopes, we can find more satellites of the Milky Way, even the fainter ones. So to date, we can count about 60 in total satellite galaxies. But it is hoped that with the new Vera Rubin telescope, we can detect hundreds more. Now, these galaxies here, shown here in these insets, are among the faintest ones, the faintest satellites. But don't worry if you don't see them very well. They're very hard to see because they're very faint. They only have a luminosity of about a few million suns luminosity, which is not great for a galaxy. So this is give you a comparison. It's just the typical luminosity of a globular cluster. So for this reason, they're very hard to detect. Now, this is a computer simulation of the formation of a Milky Way type galaxy based on the standard cosmological model. Again, this is one of the simulations built by our group. Now, this simulation took about 2 weeks to run on a big supercomputer here in the UK. It follows the formation of the galaxy right after the Big Bang until today, which is about 13.7 billion years after. It includes dark matter, which is not shown here, but dark matter is the backbone of the simulation. Now, what is shown here are the stars and the gas. So the stars are in blue on the left and the gas in red. Now, as you can see, this galaxy has a very tumultuous history. It is frequently bombarded by satellite galaxies, which disturb its stellar disk and leave a lot of debris into the halo. Sometimes we observe that the galaxy disk is almost completely destroyed, but it appears to reform quickly. So this happens because there's a lot of cold gas surrounding this galaxy, which acts as fuel for star formation. But as I said, the main driver for the evolution of this galaxy is dark matter, since it has more mass and it can do more of a damage. So every time there's an accretion event, there's also an addition of new dark matter onto this galaxy, which is incorporated into the dark matter halo of the Milky Way. So the dark matter halo grows in time. And we believe that at present time, the dark matter halo of the Milky Way possibly weighs somewhere around 1,000 billion solar masses. And that's about 10 to the 12 solar masses for reference. So this type of simulations can actually predict how many satellite galaxies should orbit the Milky Way. These predictions are so far in agreement with what is observed in the Milky Way, in Andromeda and other galaxies. So typically we expect dozens of bigger galaxies, satellite galaxies, and hundreds of very faint ones. Now this image here shows 4 such simulations of Milky Way type galaxies shown today at like a present time. The dark matter halos are shown in black and white, and the luminous matter is shown with colors. The colors are brighter when there's more stars. So as you can see, if you just compare the black and white and color images, you can see that the simulations produce many more dark matter subhalos or halos than there are luminous satellites. And this is known as the missing satellite problem. But it's not a problem because what the simulations are telling us is that not all dark matter halos may end up hosting a galaxy inside them. Now, if that is true, we expect a lot of dark matter only halos to be orbiting around the galaxy and still be undetected. They could still be felt, make their presence felt via gravity, and in principle, they could be detected by our experiments. So the advantage of computer simulations is that we don't need to know exactly what dark matter is made of in order to model it. We only need to specify that it follows the gravitational force. But there are also some simple ways in which we can mimic the different types of dark matter particles. For example, we can change the speed with which these particles travel into the simulation. Now, this image here shows some computer simulations of the same Milky Way type galaxy with two types of dark matter particles. The so-called cold dark matter, or CDM, are particles which move very slowly. And if particles move a bit faster, they're called warm. And if they move near the speed of light, they're called hot. Now, these names have nothing to do with the actual temperature of the dark matter particle. It just tells us how fast they move. Now, so these simulations show us that the galaxy with warm dark matter has fewer dark matter halos around them, so fewer satellites than in the case of cold dark matter. So obviously this will affect the dark matter signal that could be detected from Earth, from the satellite galaxies. You might ask which one is the right model. Well, we don't know for sure. We don't know whether it's cold dark matter, warm dark matter, any other type of dark matter. There's various other models. All of them can solve some problems, but also encounter some problems in comparison with observations. But it's hoped that with better and improved simulations and also with better observations, we can actually may be able to make some progress and answer what is the nature of dark matter with this type of simulations. So in conclusion, the search for dark matter continues. There are many ongoing and even planned experiments that could detect it, and hopefully they will do so in the near future. If WIMPs turn out not to be the answer, there are lots of other theories that for what dark matter might be, and there's always room for more. So if you have any ideas, please let us know. In any case, theory and experiments need to go hand in hand to have a best chance of finding it. Well, dark matter may end up being something very simple, like most fundamental laws are. For example, general relativity can be encapsulated in just a few equations. The electromagnetism laws, you can put them all down on a t-shirt. Dark matter can be something like that. We don't know. It will be great when we find it, if we find it. But I hope I convince you that searching for it is also exciting. So I congratulate you for sticking up until the very end on this long journey for the search of dark matter. I hope you'll keep thinking about it and what it means for our universe and for our place in the universe. Thank you.
Thank you, Andrea, for a fascinating talk. That's a particularly good explanation of the standard model, which is always a tricky one to get heads around and to key in particle physics with astronomy, which has such a strong link. I see we've got a couple of questions in already. Just say again, if anyone has any questions, the way you can ask questions is if you're in Zoom, there's a Q&A button, which will be at the bottom of your screen. You can click that and then type in your question. I'll also try and keep an eye on YouTube in case anyone types in YouTube questions as well. And I also noticed that Professor Brad Gibson has joined us from this morning, who's in the audience, who said he'd be interested to hear Andrea's talk. And hello, Alan. I see you've also joined again as a presenter. So we have a question from Peter Morris, who's asking, I thought the latest experiments at the LHC had more or less ruled out supersymmetry, and the latest experiments at LIGO had more or less ruled out MOND?
I don't know much about the latter, but it's true that the experiments at CERN more or less ruled out WIMPs. Yes, that's probably a correct statement, although probably people who work on WIMPs wouldn't agree with that. But obviously there's other theories. People are starting to look now into axions. And there's all sorts of theories. I haven't got the time to look into it. And obviously there's other people could talk about it. There could be extra dimensions of space or many things, yes. I don't know about the experiments in LIGO. I have to look that up.
Then we have a question from Bruce Fairbanks, and he asks, do we think that dark matter and dark energy are directly related to each other?
That's a very good question. People are thinking along these lines now more and more. There's a theory called Emergent Gravity, which is very similar to, it's along the lines of this MOND theory and modified gravity. So once you go about modifying gravity to account for dark matter, you might as well go all the way and modify it to explain dark energy as well. But it has to be very carefully done in order to explain the observations on different scales. So, because the dark matter operates on different scales as dark energy. And obviously you have to, I mean, it's not just introducing some equations which make sense. You actually have to explain what these equations mean and why the gravity should be modified this way.
Thank you.
Yeah, but if you're interested, I think you could look up for the emergent gravity theory.
We have a question in from John Morrell. As from solar system dynamics, it appears that the density of dark matter in the solar system is lower than that in the rest of the universe. Are there any theories as to why this is?
Density of dark matter in the solar system is lower than in the rest of the universe.
That's what his question is saying.
I
don't know if you have any comments on that, whether you can
confirm it depends on where
case,
how far, where do you measure this density? Obviously, on a very small scale, like the solar system, the density of dark matter is not great. You have to kind of average over bigger volumes. Now, the density where the sun is located, so you can look up where the sun is located within the galaxy. So we're located about 8.5 kiloparsecs away from the center of the galaxy, and then you could figure out how much dark matter you need at that distance. And I think the latest measurements, so people are trying to measure the local density of dark matter more accurately now, especially with the Gaia space satellite, which is able to, it's allowing us to measure the motions of stars near the sun much more accurately, so we can actually understand what's the density of dark matter. So far as I know, I think all the measurements of local dark matter density kind of agree. They're right in the ballpark with what we were measuring before. But there are large uncertainties, as we call it in physics, systematics, between different measurements of local density of dark matter. So I think probably if you're interested in the density of dark matter, you have to look at really astronomical scales, not to at such small scales as the solar system.
Yes, it's a very different way of thinking about things when the small solar system becomes something which is a bit small. Yes. We're still waiting for questions at the moment, so I might jump in and ask one, which is from your kind of work in this area, do you have any sort of pet theories or anything yourself as to what we might end up finding as to what is dark matter?
Well, I'm trying to be quite agnostic about it. Obviously, I think when I started working in this field, there was a lot of optimism that we will detect dark matter in the next 5 years and then in the next 2 years and so on. Every time was a new experiment going on. There was the hope that dark matter is just around the corner. And now I think the the feeling has changed a bit. It's not like we're pessimistic. We're just a bit more realistic of the challenges there are to detect dark matter. And obviously we learn a lot with every single experiment. I won't be able to give you an answer. I think all theories have a merit. It's not which one you prefer. It's like which one explains the bulk of observations, and some theories might explain very well some observations but not the others, so then you always have to keep an open mind.
Thank you. And we don't have a question, but we have a comment from Professor Brad Gibson. What I'm wondering is, I could read it out, but I could also re-promote Brad to presenter, if you like, and then
Sure.
he can talk. If that's, we can get to. I'll just do that now. So Brad, hope you don't mind, but I'm just re-putting you back onto the panelist list. It will probably take a few seconds for Zoom to sort itself out and re-add you in there.
Oh, yeah.
Hi, Brad.
Hi. Fantastic talk, Andrea. I loved it. It was great. No, this is way outside my area of expertise, but it was a very recent one that Peter asked that question about whether LIGO had sort of eliminated some theories around MOND. And I'd had a paper that I was editing for AppJ, which touched on exactly that. So my knowledge is very, very tiny, not very big, but it was basically the claim was that because for one of these gravitational wave events from, I don't know, a year or so ago, I've lost track when it was, there's more or less a simultaneous or near simultaneous detection of the gravitational wave event and a GRB. And because there was no significant time delay between sort of the gravitational radiation and the electromagnetic radiation, that allows you to eliminate certain extensions, if you like, of MOND, some relativistic extension to MOND, because there was no time delay between, if you like, gravity and electromagnetism. It doesn't rule out all variants of MOND, but just these relativistic extensions.
Okay.
But that's way above my pay grade, and that really is.
That sounds very interesting. Yes.
Yeah, that's the sum total of my knowledge.
Yes.
And just as we didn't have any questions, we've now had a couple come in. One from Gary Hunt, and he's asking, you said that dark matter is very stable. How has it been verified that if it does break down, what does it break down into? And could that be dark energy?
Well, it is very stable. So, well, we first have to detect it. So there's no way we could actually say that it breaks down into something else. Now it could break down into something indirectly, like for example, when they annihilate and when two dark matter particles annihilate, they basically disappear into some form of energy. Right? But it doesn't go into dark energy necessarily, because it just goes into normal energy. Dark energy is a whole different thing. Yes, I mean, I think underlying all these questions, there's a deeper question is whether we have two big unknowns, dark matter and dark energy. They're both dark. Probably there's a misnomer for both, but obviously there's two big mysteries in astronomy, and maybe there's something fundamentally wrong with something in physics that could solve both problems at the same time. I think it's quite possible that these two things are related, but in what way, I don't know.
Thank you. And we have a question from Olaf. What energy would be needed theoretically to create dark matter particles by colliding particles? Could this be achieved with the current technology, like at CERN? Yes.
Well, so that was the big hope of CERN, right? And so far, they do have amazing energies, they're very high energies, and they haven't still detected it. But they could go up the, up the energy more. It could be that the energy is outside what is the realm, a possible realm on Earth as well. We don't know. Yeah, but I think if you ask for people who do in particle physics, they would probably tell you that they need more energy. They need better experiments and look for a different, but as I said, there's actually a nice graph that's showing that the WIMPs are just a tiny bit of the energy space that could be probed, that we probed so far. So, but energy goes as mass, right? So as I told you in the beginning that there's a possibility that dark matter could be a particle, right? Which that means very little mass, right? And then they could be compact objects in our galaxy, could be primordial black holes. That would be a mass of about 10 to 30 solar masses, right? So it's a huge span in energy, if you like, and masses that we still have to probe. So many, many orders of magnitude.
Thank you. I'll just check YouTube. I don't think there's anything coming in on there.
Can I just ask a quick question, if I may?
Oh, please.
Andrea, within your talk, you said there was one particular experiment going on at the South Pole. I know that with the sort of current COVID situation, that has curtailed an awful lot at the sort of in Antarctica. Is that sort of experiment sort of affected by that? And generally, how has the sort of scientific community been able to accommodate sort of the working distance? I know astronomers are used to working remotely, but has it affected much in your field of work at the moment?
I don't know about this experiment itself, Paul. So let me say I had an image of the solar neutrino experiment. So what they're trying to detect there is that if the dark matter bumps into the sun, it will kick out some neutrinos that could be detected on Earth. So that's what they're trying to do at the South Pole. Obviously, they haven't found anything yet. I don't know about the COVID situation. A lot of experiments they need people on the ground. I am a computer scientist, so I actually can work remotely. I don't know what the situation is. It's probably affected.
That's fine, no problem at all. And Andy, have we got any more questions at all?
No more have come in on Zoom, and nothing's coming in on Facebook at the moment. So, I will just give a quick plug, which is again for Wednesday, the 16th of September, we have the next BAA webinar. That's going to be at 7 p.m. by Nick James, the director of the Comet section, and that's going to be about Comet Neowise, the bright comets we had this year. And if there's no more questions coming in, I'd like to thank Andrea once again for a fascinating talk on dark matter.